I realize we don't truly know what happens to a human in a spaceship that enters a black hole, but isn't it reasonable with the scientific knowledge we have today to assume that this guy is vapor?
I mean, it's science fiction. So a black hole is a region of space within which light doesn't come out. Nothing comes out. If you fall in, you don't come out.
Before we begin the video, a quick public service announcement. The demonstration in this video was performed on the Cisco Viral platform. In the description box, you can find the Viral file, complete with the initial configurations of all the devices. You can download this file and follow along with the steps performed in the video. Welcome back to the BGP Security series. Our series continues today with a demonstration of destination-based RTBH on iOS XE, iOS XR, and Junos devices. Before we take a look at the scenarios covered in this demo, it is fruitful to briefly go over the topology that will be utilized in this particular video. So in this video, we have divided all of our devices into 5 separate autonomous systems. There is the main autonomous system, that is AS1, and this is representative of the service provider, and this is where all of the RTBH actions will take place. So this is where we will do the remotely triggered black holing. So the other ASs are AS7, which is representative of the internet service provider. So that connects our service provider to the wider internet. And on the internet side, we have 2 more service providers, AS200 and AS201. One of these represents good traffic, that's the good guy 200, and the other one represents basically the attack traffic, so that is bad guy 201. Now all of these devices, so service provider and good guy and bad guy included, they have an eBGP relationship with the internet service provider. Now this eBGP relationship also happens to be working on dual stacks. So this is IPv4 plus IPv6. That means each of the individual links are dual stack. They have an IPv4 address, they have an IPv6 address, and over the v4 peering, so they also have 2 BGP peerings. Over the v4 peering, they exchange v4 addresses. And over the v6 peering, they exchange v6 addresses. So all of these are eBGP peerings. So every single router that you see here has an IPv4 plus an IPv6 2 eBGP peerings with the INET 7 router. The other AS is AS8. This is representative of the customer, hence the CE device there. And this has a similar condition. So it has 2 addresses on the actual link. So it's dual stack, and it's an IPv4 plus an IPv6 peering. So 2 peerings between PE4 and CE8. Let's move on to the iBGP peerings. With the iBGP peerings, we have definitely the v4 peering. But when it comes to v6, we have 2 different ways that we are demonstrating here. So between XR1, and also let's talk about the ASBRs first really quickly. The ASBRs are these routers right here. And they happen to be from diverse OSs. XR1 is based on iOS XR. R2 is based on iOS XE. And then SRX3 is a Junos device. Now all of these devices at least have an IPv4 peering with the route reflector, which every other device here is an iOS XE device. So RR6, P5, P4, and CE8, everything else that is not an XR and SRX, apart from those 2, everything else is an iOS XE. So all of the ASBRs and the PE, they all have an iBGP IPv4 relationship, at the very least, with the RR6. Now for all of the devices other than R2, this also happens to be IPv6 NLRIs learned over IPv4, and then we are tunneling them through MPLS, so this is 6PE If you're not familiar with 6PE, just imagine that you have a single iBGP peering, that's an IPv4 iBGP peering, and over that iBGP peering, you are also exchanging IPv6 routes. So you exchange the IPv4 routes just as you would normally do, and then you exchange IPv6 routes over that IPv4, but you also exchange a label with it, an MPLS label. So it is using something similar to what you would use for L3 VPN. But at the end of the day, you're going to tunnel the IPv6 traffic over the MPLS infrastructure. And then you use the IPv4 peering to exchange your control plane information. R2 is special in this regard. So R2 has a GRE tunnel. So R2 has a GRE tunnel with R6. So R2 and RR6 have a GRE tunnel. This GRE tunnel is IPv6 over IPv4. So you are essentially exchanging IPv6 routes over an IPv6 peering. So there are two peerings between R2 and RR6, and you are exchanging IPv6 routes over the IPv6 peering and IPv4 NLRIs over the IPv4 peering. Next, each of the devices, at the very least the ASBRs, maybe the PE, but at the very least the ASBRs, have two pre-configured static routes. So there is an IPv4 static route. This was the 192.0.2.1 static route /32. And with IPv6, there is another similar address that has been reserved for IPv6 discard routes, which is out of the 100/64, so we are just going with 100:1/128. And both of these point to a discard route or a null 0 route. So that means if we set the next hop of any NLRI to one of these addresses for IPv4 or IPv6, we will be able to get a BGP discard route. And this is functional on the ASBRs. And apart from that, just to save time in the video, all of the route maps have been predefined already on all of the relevant devices. They have not been applied. And when I say route maps, I actually mean route policies, policy statements on the SRXs, and plain route maps on the iOS devices. But all of those policy elements have been pre-configured on all of the devices, and we will be looking at their application rather than waste time typing them. So now that we have all of this covered, let's go back and take a look at our first scenario. So our first scenario happens to be the next hop attribute-based RTBH. So you change RTBH, or you implement RTBH based on a next hop attribute change. And then there is a sub-scenario there where you use an actual trigger router to do this. So without further ado, let's go ahead and do this. So remember the scenario. And before I do that, the trigger router also happens to be the central router here. So the trigger router is going to be RR6. This is our trigger router. And with this particular scenario, remember the customer is going to call the NOC. And the NOC, or the customer is going to go to a web page. Either way, it's going to supply one of its own IP addresses, one of the IP addresses that is advertised by the customer. And then the trigger router is going to introduce that IP or IPv6 address into the service provider network. And that's how it's going to be black-holed. So let's go ahead and verify some base connectivity. On CE8, there is an address. There are a few addresses, but all of them happen to be within the 8.8.8.0/24 range. And there are specific addresses, I believe, 8, 9, and 10. So all of those specific addresses happen to be in here. And one of them is going to be black-holed, and we're going to pick 8. So let's go ahead from the good guy AS and the bad guy AS. Let's verify some connectivity. So it's going to be ping 8.8.8.8, source loopback 0. Now there's loopback 0 to loopback 0 connectivity only on these. And then 8.8.8.9 and 8.8.8.10. So all of those are reachable by the good guy. How about the bad guy? So we'll go ping 8.8.8.8, source loopback 0, 9, and 10. So there is end-to-end connectivity between these devices. Also, there are IPv6 addresses defined here, and those IPv6 addresses all happen to be within the 2001:8:/64 range. And once again, we have 8, 9, and 10. So let's go ahead and verify a couple of these from good guy and bad guy. So we'll say ping 2001:8:8. And again, this has to be sourced from the loopback 0. So let's go ahead and source it from loopback 0. How about 9? And then 10. So right now there is no RTBH in the core. So, and again, ping 2001:8:8. We have to remember to source from the loopback because the other addresses are not advertised. 9 and 10. So we have that sort of connectivity. The next thing that's going to be, that we're going to pretend in the scenario is this .8 address for both IPv6 and IPv4 is under attack. So we have to isolate this address without black holing any of the other traffic. And then the way we are going to do that is we're going to use the trigger router to introduce a /32, but also we have to make sure that we are using the scenario where this is next hop attribute based. So we have to make sure that the route map actually changes the next hop attribute instead of the community. So let's go ahead on RR6. There is a route map predefined here. We may have to change it between the community and RTBH or next hop attribute, but let's go ahead and see the route map. So we'll say show run section route map. This is an iOS device. And as you can see, what this is trying to do right now, this is a route map that is going to be applied to a static route because that's how we are going to originate the route. It is going to look for any static routes that have a tag of 666 applied to them. So we will see how to set up a static route with that tag applied. If it sees that tag applied, it is going to manually change the next hop to 192.2.0.1, which, as you can see on the ASPRs, is a discard route. I have set a few other best practice things here as well. So I've changed the local preference to 200. So if my local preference is 100 by default in the entire SP, then this route becomes a little bit more preferred. And we are always making sure that even if it's not the most specific route, it is still going to be more preferred. I've set the origin to IGP, and that is mostly because when you redistribute a route, as we are going to redistribute in iOS, it actually is originated with an origin code of unknown or a question mark. So I wanted to make sure that this looks like an IGP route because that's where it's coming from. It's coming from a static route. But we are not using a network statement. That's why I'm manually changing the origin to IGP. And finally, we don't want to leak this route outside our AS, so it's going to be a no export route. Finally, if there is no match on tag 666, I don't want to use this particular router to introduce that route, so there is a deny 20 statement. For V6, pretty similar. Everything is almost exactly the same, except there is an IPv6 next hop statement this time, and this is setting it to 100::1, which also happens to be the null route or the discard route for IPv6. Before we introduce this route into our network, let's take a look at all three of the routers as to how they are routing for 8.8.8.0. So on iOS XR, if I say show BGP IPv4 unicast 8880/24, or let's just take a look at the table first. And as you can see, there's only one route from that range, and that's a /24 route. Similarly, for IPv6, there should be one /64 route from 2001:8, and that is true across the board. So this is the same route, or the two same NLRIs that have been advertised to all of the other routers. So we can check this on R2 really quickly. Show BGP IPv4 unicast. Show BGP IPv6 unicast. Similar information. And you can see the information on for IPv6 is actually, the next hop is an IPv4 address. It's a little bit more obvious on R2, but this is what 6PE routes look like. So they're going to recurse down to a label. Finally, on SRX3, show route protocol BGP. And we can see 8880 is right here, and then 2001:8 is right here. The static routes are also here, so show run router static on XR1. So you can see there are those two routes for null 0. Show run include route, and there are those two routes. And finally on SRX, it's going to be show run or show configuration routing options. And there are those two routes in INET 6.0 and then INET.0. Both of those static routes are there. So on RR6, now we have to make sure that 8.8.8.8, the traffic from that is discarded. So let's go ahead and bad guy and start a round of pings to 888.0. And let's put a high repeat count on here so we can see that on the screen as we bring the RTBH in. So on RR6, do show run section R BGP. It's very simple BGP right now. There is nothing really happening on here other than that 6PE. So we're going to go into router BGP1. We're going to go into address family IPv4. And now what we have to do is we have to redistribute static routes. And this is not per se for 8888, but this is basically just to implement the whole scenario. Then that way, anything that we tag with 6666 will be black hole. So we'll say redistribute static, and there's going to be a route map on it. Let's look at the route map name, which is RTBH v4. And that should be it. So we don't really need to set a metric here. But right now, as you can see, nothing really happens because we don't really have a static route. So yeah, the only static route we have is to resolve that discard next hop. So, but that one is not tagged with 666, so we are not redistributing it. Now we need to create a static route for 8888. 255, 255, 255, 255. It is going to be to null 0. And that really doesn't matter because the route map changes the next hop anyway. But the most important part here is the tag has to be 666 so that the route map can see that tag and it basically is processed by the route map. So once we do that, you can immediately see that the traffic has stopped, and what's happened here is do show BGP IPv4 unicast. The trigger router or the route reflector has introduced a new NLRI, a /32, which is more specific. It's got a local preference of 200, but especially the next hop is now 192.0.2.1, and that when it goes out to these routers, it will end up in a discard route. So let's take a look at it. Show Ceph 8.8.8.8. And it is not actually right here. Null 0 JNCIE, so that route is being dropped. Similarly on R2, if I say show IPsec 8.8.8.8, because of that next hop, it is now resolving to a null 0 route. And then finally SRX3, if I look at protocol BGP, hopefully 8888, I can see that this is also a discard route. So all three of them are processing it as discard routes. Now some of them are dropping it silently. It looks like one of them is not dropping it silently. And also on INET 7, just to make sure that all of the ASBRs are used, I am using BGP multipath here. So if I say show BGP IPv4 unicast, obviously the 8888 is not going to be advertised because of the no export community, so this is a good verification for that too. But there's also multipath that is load balancing this traffic across XR1, R2, and SRX3. Now this should not have affected anything other than 8888. So the other addresses on that network, they are still reachable. And similarly for 10. So those have not been affected by this. What about the IPv6 addresses? So they are obviously, so far they haven't been affected, but what if we did want to do that? So 8888, let's source it from loopback 0, and let's again put a high repeat count on this. So as you can see, 2001 8::8 is still accessible. We're going to do the same thing here on the trigger router. We'll go to router BGP1. Address family IPv6 this time. We'll say redistribute static, route map, RM, RTBH, v6 this time, and that should be it. So once again, once we're finished with that statement, we actually have to bring in the route. So this would be IPv6 route 2001 8::8 /128, so that's akin to /32. This can also be pointed to null 0, but we have to make sure that the tag is 666. And once the tag is 666, as you can see, that route is being discarded, or that traffic is now being discarded. But this works a little bit differently depending on if your scenario is 6PE or if your scenario is IPv6. So 6PE is working on XR1. So let's take a look at what this route looks like on XR1. So if I say show BGP IPv6 unicast, you can actually see it doesn't really make a difference. It's as if the route is still being originated from RR6. So if you look at a previous, or actually if we compare it to the /64, that's coming from PE4. This is coming from 6666. And that's because, at least in the case of iOS or iOS XC, when you advertise an IPv6 route across 6PE, so when you advertise it with the label across the IPv4 peering, it doesn't really matter what the local next hop was set as. It is going to be massaged into an IPv6 compatible IPv4 address, so it's going to be, it's not obvious here, but it should be more obvious on R2. Actually, it's not going to be obvious on R2 because that's not a 6PE device. Let's look on SRX, if that's a little bit more apparent here. And let's look at the details of this. And it is. So it is going to be massaged into this format, which is basically the last 32 bits have been imposed from IPv4, but it is : quad F and then the IPv4. So it's an IPv4 compatible IPv6 address is, I believe, what it is called. But regardless of that, whatever next hop we were setting on RR6, so on RR6, do show BGP IPv6 unicast, this is being set correctly. This is 100::1, but once we advertise it over 6PE, it goes back to this particular address, which is IPv4. So what is happening now is that this traffic is being received from INET 7, and once it comes to XR1, or it comes to SRX3, XR1 and SRX3 are still using 6PE to get this traffic across to R6, and then on R6 this traffic is being dropped. So that's a little bit of a subtlety, but that is what is happening in the background. Now for R2, it's a little bit different. So for R2, if you look at the BGP peering for R2, it's different for IPv6. Show BGP IPv6 unicast summary. And you can see that with 6.6, I actually have an IPv6 peering. And where is this address? Show IPv6 INT brief. I have a GRE tunnel that exists between R6 and R2. So what's going to happen here is when I look at that actual route, show BGP IPv6 unicast, this time, because it's not 6PE, it's just native IPv6, the next hop trigger actually does work. So if I look at that route in Ceph, so if I say show IPv6 Ceph 2001 8::8, I actually see that being discarded. Whereas on XR1, it is not being discarded. Show Ceph IPv6 2001:8:8, it actually is going through 6PE. So it is going across to P5, which is going to send it to RR6, and then it's going to get dropped on RR6. So subtle, yet very, very important to realize that it works differently with 6PE. So it can obviously work, but all of the traffic is not being dropped on the edge. It is being dropped on some internal router, which may not be fruitful, or which may not be something that you want to do. Finally, on the bad guy, let's take a look at the other addresses. Are they reachable? They still should be. There's no reason why they shouldn't be. So they are. 9 is reachable and 10 is reachable. So all that is well and good. That brings us to the end of scenario 1, except one important thing. And we may have missed this, but I want to make it explicit. This traffic, this victim, is now completely offline. So to the good guy and to the bad guy, this victim is now completely offline. Both for IPv6, but also for IPv4. So completely offline as far as the victim is concerned. The next subsection of the scenario still uses the next hop attribute manipulation to provide RTBH, but instead of the customer having to go to the NOC, the customer will just be provided with a community this time. And they will use that community to signal in. So in this case, all the provider has to do is figure out which community would they like to accept from the customer, put some restrictions on it, some restrictions that will make sense in a minute here. But essentially, that's all they have to do. Once the customer introduces a route or advertises a route, tagged with that community, that route will be black-holed. So let's talk about the community first. It's going to be 1:666. So this is the AS number. This is that 666 semi-well-known RTBH discard community. And we're going to accept that from the customer. We're going to put some restrictions on it. So now the customer should not be allowed to black hole wide variety of or vast range of addresses. So we're going to put some restrictions on it. For IPv6, we are usually accepting a /24 for the customer and no longer prefixes. But for RTBH, we are going to make an exception to this. As long as it's an RTBH route, we are going to accept anything all the way up to /32. So /24 to /32. Similarly, we are going to accept /64 to /128 on IPv6. We're also going to restrict it to the customer's prefixes. So usually for this customer, I am accepting 8.8/16. I'll keep on accepting those unless until they are tagged with RTBH. Then it has to be a little bit more specific, and it can be a lot more specific. But for the regular routes, I'm not going to accept anything more than a /24. That's very common SP type practices. Similarly, a /32 is being accepted for IPv6, But if it has to be any longer than that, then it has to be tagged with the RTBH community. Finally, a note about 6PE in this. This scenario just did not work well with 6PE, at least with my router, which happened to be an iOS XE, for a myriad of different reasons. Anytime I manipulate the next hop on the incoming eBGP route, the next hop just becomes inaccessible because of that discard route, and it is no longer advertised. So what I'm doing is I am checking for the community as the route comes in, but then I am manipulating the next hop as the route goes out to the route reflector, but that simply just doesn't work with 6PE. Once I manipulate the next hop, the label stops getting advertised and it's no longer working, so we'll skip this scenario for 6PE at least. So let's go ahead and take a look at what the PE looks like for this case. So we'll say show run section route map. And let's do this. Let's look at these one at a time. So route map for v4 prefixes or v4 NLRIs. And I can see that there is a route map towards the CE coming in. And on this, what I'm doing is I'm matching a prefix list, I'm matching a community. If that matches, I'm adding the no export community to it, and I'm also manipulating the local preference. So as you can see, this is similar to what we did on the trigger router. There's also a permit 20 statement here, and that is a catch-all for this other prefix list. So what does this prefix list look like? Let's look at that. And the prefix list for RTBH routes, so those that are tagged with the RTBH community, that prefix list happens to be 8.8.8, so still within the customer space, but anything between /24 and /32 is accepted. If it is not tagged by that community, my standard admission practices are 8.8/16, but then I will accept prefix up until /24, but no longer than that. So as you can see for RTBH, I am making an exception here. Similarly, if you look at this, pause the video and you can look, it's the same concept for IPv6. The second part of the route map is the route map I'm using towards the route reflector. And in this, I'm matching the community for, once again, the RTBH, the 1:666, and we can take a look at that as well. Show run include community. So there is a community list that is permitting 1:666. So the CL-RTBH is a community list for RTBH, and this basically matches 1:666. Also, this command is required on iOS XE to display the community in the AS:/NN format. Otherwise, it'll just dump a 32-bit decimal number towards you, and it's not going to look pretty. But what I'm doing towards the route reflector then is I am matching the community. And if the community matches, because remember, this no export is additive, so I am adding the no export, so the original community survives. And if so, then I'm manipulating the next hop to 192.0.2.1. It's as simple as that. And then again, I'm not doing this for v6 at all. So I'm accepting the community for v6, but I'm not manipulating anything with the next hop attribute manipulation, because that simply just is not something that is workable. On the CE then, I need to introduce the route with that community. So let's see what I'm doing on the CE for now. Show run or show BGP IPv4 unicast. So as you can see, I'm originating an 888/24 route, but how? So show run section RBGP. And this route is being picked up with a network statement. So that means the route must be in the routing table. So if I say show IP route 8.8.8.0, I can see this is just simply a static route pointed to null 0. But I still have prefixes. So if I say show IP INT brief include loopback, I can see that I have specific /32 prefixes that I'm accepting traffic on. So this is just a catch-all to advertise BGP, but then these are the actual routes that respond. So if I go on, for example, bad guy again, ping 8888, source loopback 0, that 8888 is actually hitting this loopback 0. So that's the static null route is, the bit bucket is just for advertising the traffic. Now, how do I tag the routes with the community? Well, again, it's going to be with a route map. And the route map in this case is very simple. If it is applied to a redistribute or a network statement, then it's going to set the community 1:666 and nothing else. That's the only statement, and it matches nothing. So the way we can do this is we can go to router BGP 8, address family IPv4 unicast, and then have a network statement for 8.8.8.8, mask 255.255.255.255. But before I press enter, I'm going to pass it through this route map. And this route map was RM RTBH CE. Once it passes through the route map, it should have that community applied to it. So do show BGP IPv4 unicast 8888. And the community applied is right here, 1:666. So now on PE4, I should be receiving that community. Show BGP IPv4 unicast 8888. And there is that community. And then this is my additive community on it, which is the no export community, so that I don't leak the route. So a moment ago, bad guy had access to this route. Let's see if they still have access to it. Well, they no longer do, because so right here, the next hop is still okay. But remember that route is still going to pass through the route reflector route map, and it is going to manipulate the route, the next hop to 192.0.2.1, creating a discard route. And we have to take a look at it here. So if I say do show BGP IPv4 unicast 8888, what I'm receiving from 4444 is the next hop of 192.0.2.1. It's going to have the same effect on XR1, etc. So let's take a look. Show Ceph 8.8.8.8, and the next hop is 192.0.2.1, which is a null 0 adjacency. So we have explained this in the past, so that brings us to the end of this scenario. Last thing before that, I just have to make sure the route is not being leaked, but why should it? We trust the no export community, so show BGP IPv4 unicast, and the internet is none the wiser as to what we are doing, which is basically dropping the traffic on the edges. Ping 8889, source loopback 0, anything else on that network is still accessible. So that's all we are doing with that second scenario. That brings us to the next scenario, which is the community attribute-based RTBH. In this case, we are letting the local routers, the ASPRs, take the decision as they seem fit. And we are basically just advertising them routes for the community, and there's going to be local policies on the ASPRs looking at specific communities and discarding the routes based on those communities. So the first subsection of this is trigger router originated. And in the trigger router originated scenario, we're basically going to, instead of advertising the next hop, just advertise the community this time. So the route is still going to be triggered on the trigger router, the RR6 router, but we are going to change the route map so that we are not manipulating we are not manipulating the next hop this time. So let's take a look at the route maps. So section route map, and both of these statements are going to go away. And then the set community now is also going to be, there's going to be another community added to no export, which is going to be the RTBH community, which I'm keeping as 1:666. So let's manipulate v4 first. deleting the next hop statement. This is going to be gone. And then in the set community statement, I'm going to add 1:666. So let's look at the route map again. And as you can see, so this is a good example of what happens when you don't have the new format command. This is now dumping in that 32-bit number. So we'll change that in a second here, but first I want to quickly manipulate the v6 similarly, deleting the IPv6 next hop statement, and then adding the same community statement, which we can basically copy paste. So exit IP BGP community new format. Now when we look at the route maps, they should look a little bit better, depending on what you call better. So 1:666, 1:666. Rest of the stuff is similar. I also want to stop advertising that route. So 8888 we were black holing from the customer, so I want to take that out. Do show run section R BGP. So on the customer, go into router BGP, address family IPv4, and basically take this network statement completely out so that we are no longer black holing the traffic, at least from the customer, which allows us to black hole it from the trigger router. On the bad guy, let's make sure there's connectivity restored, which it is. So now on our R6, actually there's one more thing. So what happens once the route gets originated with this community? We'll show you the local policy in a second here, but let's introduce a couple of routes here. So again, this is going to be IP route 190, or this is going to be 8.8.8.8, 255.255.255.255. And you can literally have any next hop here, so I'll just use null 0 because that's the treatment that we want, as long as we are tagging it with 666. Similarly, IPv6 route 2001:8:8/128 to null 0, as long as it's tagged with 666. So do show BGP IPv4 unicast. There's that first route, the second one in the list. And do show BGP IPv6 unicast. That's again the second route on the list. We just want to see the communities as well, 8888. So now there are two communities that are added to it. The new no export community and 1666 community. For IPv6 unicast 2001:8:8/128, same thing. There are the two communities, and that's literally the only thing. Other than the local preference and the origin, those are the only two things that are changing here. Now a look at the policies. So on XR1, let's look at the policy that we have applied towards RR6. Show run router BGP. So router BGP towards 6666 right now has no policies. Actually, I've defined the policies already, but they've not been applied yet. So let's look at our routing policies. Show run route policy. And the two particular ones I'm interested in are the iBGP v4in. This one says if the destination is in 0000, so any destination, but once again, I'm putting that restriction on the prefix length. The prefix length has to be between 24 and 32, and it matches community 1:666. So that community has to be there. Then I'm basically programmatically setting the next hop to discard. If it doesn't match this above criteria, then the route is accepted as is. Similarly for v6, I'm accepting any route, but the prefix length has a restriction on it, 64 to 128. But then again, there's the community, set next hop discard, else pass. So what would we have to do? We'd have to apply this community inbound, because right now we should not really be black holing any traffic. Well, it looks like we are, and that might be, so it's probably black holing from somewhere, but I'm not 100% sure where. So let's take a look at the route as it's received here. Do show BGP IPv4 unicast 8888. So this should really be forwarding that traffic. So if I ping locally from here, and I really don't have any addresses that ping actually I do. Do ping 8888 source loopback 0. It looks like it is being black hole, but that could just be a return path problem here. We'll let this run for a second, but I want to see if any of the other routers have that route map already applied when it was not intended to. So this one doesn't, and what about the SRX? So this one doesn't either, but it could be because, actually I know why that is. So right now the route is being discarded on RR6 because remember, who is originating this route? RR6 is originating this route. So the route reflector now ends up being in the data path. And because it's in the data path, because the next hop is the route reflector, the traffic then is going to be sucked into the route reflector, and on route reflector we are still pointed to a null 0. So this is effectively working, but this is working not on the edge of the network, this is working in the middle of the network. So let's make it work on the edge of the network, which is by applying those policies. So show run router BGP1 address family or neighbor 6666. And all we have to do is to IPv6 labeled unicast and IPv4 unicast, we have to apply those policies. So let's go ahead here. Address family IPv4 unicast. The route policy is going to be the RP IBGP v4 in inbound. So as I receive routes tagged with that community, I want to set them to discard. Similarly, I'm going to do this for IPv6 labeled unicast, but just change the policy to v6. So committing the config. Now if I say do show ceph 8.8.8.8, I should see the null 0 adjacency. So now I'm not dropping in the middle of the network, I'm dropping on the edges, which is the desired behavior for me. Also for 2001:8:8 slash or ceph IPv6, I believe is needed here. And once again, this is null 0 adjacency, so I should be dropping the traffic. Well, the traffic was dropping already from before, so this is really not a good display of this. But at least now we are sure that we are dropping it on the edge, at least on the XR. We'll drop it shortly on the SRX and RA2. So again, those two destinations are black holed for reasons that we understand. On R2, it's a route map that we are using, show run section route map. And once again, it matches the address in the prefix list RTBH, it matches the community, and then it is setting the next stop. So remember, iOS XE still doesn't allow you to programmatically set the next stop to discard. So you have to set it to a next stop that is then statically pointed to null 0. But let's take a look at the prefix list and the community list. The prefix list here is, and once again, we are not using the new format, but this number should be familiar. It is 1:666. But when it comes to the prefix list, we are accepting any routes that are greater than /24 and any routes that are any IPv6 NLRIs that are greater than /64. And then again, after that, we have a permit 1000 on both of these, so any other routes we are accepting unmanipulated. So config T, router BGP1, address family IPv4 unicast, and on the neighbor 6666, for this family we're going to say route map RM IBGP v4 in inbound, And then address family IPv6 unicast, we're going to have the same statement with the v6 map. Remember, this is not a 6PE scenario, so I have a different address for IPv6 peering here. So do show run include neighbor. So the neighbor is now on the GRE tunnel, which is this one. So 66, and then I'm going to say route map RMIBGP-v6 in. So on iOS XE, at least you have to clear the routes. Do clear BGP IPv4 unicast star soft in. Similarly with IPv6 BGP star soft in. And let's look at the final result here. Do show BGP IPv4 unicast. As you can see, 8888 is now pointed to the null next hop. And do show BGP IPv6 unicast. You can see that this is also pointed to the discard route. So everything is working here now. This is much more powerful, right? You can tag with different communities. You could have some zone-based RTBH. You could really have some complicated setups if you're using the community-based RTBH, also inter-provider and inter-AS. Finally, on SRX, show run or show configuration policy options. Similar things here. The community RTBH contains the 1:666. The first one has a route filter, which is pretty much like the prefix list, but the route filter accepts anything as long as the prefix length range is 24 to 32. Similarly, for family INET 6, any NLRIs as long as the prefix length falls between 64 and 128. And then again, the next hop is being programmatically set to discard. So let's look at show protocol BGP and then set it up for group iBGP is what it's going to be set up for. So we'll say edit protocol BGP, edit group GPI BGP, and then in this group for the neighbor I'm going to have an import statement. So for neighbor 6666, set neighbor 6666, I'm going to have an import statement, and in this import statement for IPv4 I'm going to use this, and then for IPv6 I'm going to use the other policy. So let's go to the top and do a quick show compare, and what you should see is both of those policies now should be inline. So every route is going to be passed through the first policy. If it's not going to match with the INET 6 family routes are not going to match, it's going to be passed through the second policy. Let's go ahead and commit this config, and meanwhile let's go ahead and test this here if this is still working. It looks like it is. And are the other victims online? They are. Well, not the victims, right? So hopefully they're not victims. But on SRX3, let's look at show route or run show route. And this should show us for 8888. Now we are discarding. And also for in table INET 6 for 2001 8:8, we are also discarding. So now all of the traffic is being dropped at the edge instead of the middle of the network. Finally, the last scenario in which we're going to use the community attribute to signal RTBH, but the customer is going to signal it. And believe it or not, our network is already set up for this. So realize this, we are already accepting a community for 166. We are treating it a certain way from the customer on the PE. The PE reflects it to the route reflector, and then the route reflector sends it over to the edges, and they also receive the same community. So now instead of the route reflector originating the route, let's originate the route from the CE itself. So for that, we'll have to go to the route reflector and delete those two static routes. Include route. So we'll delete the 8888 route. And we will delete the 2001 8:8 route as well. So both of those routes are gone, which means the traffic should be flowing again. So let's try 8888 with source loopback 0. That's working. And 2001 8:8 also with source loopback 0, which is also working. So everything is working right now. And what we should have to do simply is start the signaling from the customer. And the IPv6, I'm not 100% sure about. We may have to tinker it, but IPv4 should be working right now. So on the customer network, we basically have to just bring back this network statement again, which was with the route map, which is this one. So once that statement's here, do show BGP IPv4 unicast. It's here. Let's take a look at the bad guy. That's the IPv6 address. So it's not working right now because on all XR1, XR2, and XR3, it is the same exact scenario as before. It's receiving those communities, and then it is pointing it to a null zero adjacency. But just that the community is now being originated from the CE instead of the trigger router. So let's try address family IPv6 unicast. And this is going to be network 2001 8:8/128. And this is going to be with a route map called, it's just RTBH because all it's doing is it's slapping the community on it. Do show BGP IPv6 unicast 2001 8:8/128. And now the community is there. So what's happening on XR1? Do show BGP IPv6 unicast 2001 8:8. And as you can see, we are receiving the community, and it is being the no export community is being added to it. So now if I look at the CEF IPv6 2001 8:8, it is a null zero adjacency, so it should be dropping traffic at least on XR1. What about an R2? Do show BGP IPv6 unicast 2001 8:8/128. And once again, I am receiving the RTBH community. Let's make it a little bit more explicit. IPBGP community new format. Take a look at the NLRI again. And this is 1666, so it should be now dropped as well. So do show IPv6 CEF 2001 8:8. And it is being dropped to null zero. What about an SRX? That's the final piece of the puzzle here. Do show route INET 6.0 or table INET 6.0. And we are receiving that route, and it is a discard. So you can see once everything is set up to receive the community from the customer, make the checks on it, spread it throughout your network, and dropping traffic on the edges is not that hard. And with that last one, all of our scenarios are covered, and that's it for this demo. And in fact, that brings us to the end of the video. In our next video, we'll discuss the topic of source-based RTBH in depth and finish it off with a live demo. Till then, I hope you've enjoyed this video, and I'm looking forward to the next one. Thanks.